Next, we'll be having an AI workshop brought to you by Michael Batavia. Michael is an incoming freshman at the NYU Tangent School of Engineering, a Regeneron Science Talent Search semifinalist, and a prior executive director of the leading hackathon in Long Island, Teen Hacks LI. Michael is directly interested in using machine learning and deep learning with the medical fields to solve pressing problems, including pre-diagnosing breast cancer from histology images, creating a device to help the blind navigate large metropolises, and diagnosing real and fake medical news. Consequently, he is interested in making his own startup in the near future in order to intersect the roles of app development, artificial intelligence, and biochemistry to automate these tasks and make them more available to help patients nationwide. Check him out on LinkedIn and GitHub. Without further ado, let's get to this workshop.
Hey everyone, thank you for having me. And yeah, it's a real pleasure being able to host a workshop here. So thank you to both of you for inviting me. I'm just going to start up the presentation and we'll begin shortly. All right, so welcome to my workshop. This is the key insights of using deep learning to analyze healthcare data. As Sahana introduced, I'm Michael Batavia. And yeah, you got this cool deep learning kind of background going on. Let's just get started. So the first thing you might be asking is, who am I? And why am I at the Brooklyn Bridge presenting this workshop to you? Well, as Asana just said, Michael Batavia, freshman at NYU Tangent School of Engineering. My specialty is doing research projects with machine learning. I've done several projects with machine learning and deep learning. I've won awards for it. For those who don't know, the Regeneron Science Talent Search is a pretty prestigious competition that is held annually for high school seniors. And after working on a project devoted to detecting whether breast cancer lymph nodes were benign or malignant, I managed to become a semifinalist. I was also the 2020 Congressional App Challenge winner in District New York 14, which is a app challenge that Congress runs each year, and I used artificial intelligence in a part of that project. And I've also done full-on data analysis. Data analysis is a part of machine learning. It's often done as a lot of pre-processing steps that are quite important. And I've done a whole analysis on avocado prices. So you'll be safe to say you're in safe hands when you hear me talking about machine learning and deep learning. And yeah, I'm going to teach you the best data analysis tools to deal with real-world complicated healthcare. So are you guys excited? Because we're going to get started. All right, so the first thing we're going to be starting off with is asking the question, what are we looking for? Before we even begin to describe any techniques or any steps that we need to use, we need to actually begin to define our data. So we're gonna think about the types of data we might have. And I'm gonna ask a question to you guys. What are possible data inputs that you might need to pre-process when you first obtain your healthcare data? Like when someone tells you, I want you to use some neural network to analyze this health data, what type of data might you get? So you can unmute your mic, or you could say something in the chat. Take a couple minutes for you guys to give me your thoughts.
So we have some answers in the chat. We have pictures and videos, remove private data, data on previous surgeries or treatments, MRI scans.
Yeah, those all are very good answers, especially pictures and videos. Those are going to be very important because, if you're looking at a cancer cell, you're going to want an image of it. And, that's often what you get in healthcare data. Removing private data, that could be useful to some degree, especially data on previous surgeries and treatments. That's a very good answer, because usually the data on previous surgeries and treatments often affects the current. So for example, if you have COVID-19 and it's known that you have high blood pressure and you've had diabetes before, that could be a sign of like more ill symptoms to come with COVID-19, because it's shown scientifically that diabetes could lead to COVID-19. But don't trust me on that. I'm not a doctor. And MRI scans is also a very good answer. So nice job to all of you who answered. And exactly that's the type of data that we need to know. We kind of need to know what we're handling before we even begin to handle it. So here's some other types of data we might be given. We have ECG charts. We have ECG charts, so you know that line that spikes and it shows whether a person is alive or dead. You might have seen that in movies. We have slide images of metastatic benign lymph nodes. So breast cancer, lymph nodes, you can slides images. You have a chart containing various serum measurements from diabetes patients. You could do some good old data analysis on those numbers. You have JPEG ping photos of cancerous tumors just straight up given to you. You might have a chart containing various physical attributes of a patient, like height, weight, BMI, muscle mass, body fat. Or you might have maybe some test measurements for prosthetic limbs for veterans. So, there's a whole different a lot of data you could be given. You could be given straight up numbers, you could be given images, you could be given videos. But the most common type of data are usually going to be charts containing numbers. Like one of you guys said in the chat, like data on previous surgeries, or you could be given images or video, most commonly images. So for this workshop, I'm going to talk to you about using data analysis and deep learning on images, because I used images for my Regeneron Science Talent Search project. And if you go on like a cancer database, most often you're going to find images. So you need to know how to deal with images before you start dealing with more complicated things. Now, when you're working with images, it sounds pretty simple, but you're going to need to know how many images you have on the topic and what file format the images are. So like how much data you have. You could have 100 images, you could have 1,000 images, you could have 1,000,000 images, but knowing how much data you have is important for neural networks, because neural networks tend to like a lot of data, and it's going to be a problem if you only have 50 images. And the file format has to be very common. Like you can't have some unknown file format that you're sending to a neural network like SVS or I don't know, DMG. You need to convert those images into something that's more recognizable, like JPEG or PNG or GIF or a bitmap, something very recognizable. These are some common types of images you might want to convert to: JPEG, PNG, SVG. It stands for scalable vector graphics. It's pretty good. And you have GIF, and I'll just create a nice file format graphic for you. So images, how much you have and what file format. You need to convert your images to the most applicable file format, and usually one that is most general. The next step is organizing your data. So once you have converted your data to an appropriate file format, so you could do this via online tools or programming APIs, you need to know how to organize your data. So here, I'm going to present you guys another question. If you have a bunch of, let's just say, breast cancer data containing various pictures of metastatic and benign tissue and their corresponding labels, what I mean by labels is basically a number 0 or 1, where 0 means benign and 1 means malignant. How would you organize the data? So you have a bunch of images, you have a bunch of labels. How would you organize it? And excuse me, this may sound very simple, but it's good to organize anything before something some problems start to arise. And remember, guys, that there's no exact wrong answer. It's not like you get punished if your answer is completely wrong. In programming, you can have various degrees of ideas, and you have your own creativity to implement them. All right, I'm going to just look in the chat. So Smiley, I believe, you can correct me if I'm saying that name wrong. That's actually a pretty good idea, making different folders and compiling them. I've seen a lot of analysis on healthcare data, make different folders and put the different, like, benign in one folder, malignant in another folder. So you already know, benign, which photos are benign tumors and which photos are malignant tumors. So that's a very good technique. You might see that around in some tutorials. And yeah, I think Arav also got the same point, organizing the data in groups. Another alternative thing you could do is you could make a CSV file containing, in one row you would have the file name, and then in the other row you would have the label. So for example, you might have like benign cancer 0.png in one column, and then the other column you have like 0, meaning benign. But also those techniques that you guys said, those are also very common. Now, you may have already organized that data, which is very good. Organizing the data is really great, and separating it into benign and malignant categories. But it's also very good to visualize your data. You might know what you're working with. So I might know I'm working with a ECG chart reading, or I'm dealing with images of lymph nodes. But do I really know what I'm looking at? That's the question. That's why it's important to visualize the data. So here you have a image from a research paper containing, I believe, some analysis of tumors. So you have H&E, which usually refers to like tumor slides, scans. So you need to know, like, now I kind of know what I'm looking at with tumor cells. And here's another example of some data you might be working with. This one is plotted. So the researcher did a pretty nice job understanding the data and creating some graphs to signal what the data represents. So you could visualize your data just by straight up looking at it, or you could create graphs to represent the data. It's up to you. I would recommend just looking at the data first before you do anything complicated with it. All right. Now, we organize the data. We also understand what the data represents. So we know what the lymph nodes look like. We've separated the lymph nodes into benign and malignant categories. But now we need to let the program know what we're doing. We need to actually start our data analysis. And we do this by loading in the data. And you could do this in a desired programming language. Most commonly, it's done in Python, but I've also seen books do it in Java. And here are some tips. Feel free to write this down. So if you use that CSV file idea I said, where you have one column the file name and the other column the label, you could use imaging libraries like PIL, which stands for, I think, Python Imaging Library, to convert the file name into the actual image, like read the file name from the directory and get an image back, and just replace the file name with the image. So that way you have a one-to-one mapping between the image and its label. You could also do that idea that you guys said by putting the images into different folders, and then you could read the images from a directory, and just keep in mind that the directory that the images came from, the name of that directory corresponds to their label. So, there's different options. You could use the CSV file and load the images from the file name, or you could just load the images straight from the directory, but finding the label for the images is going to be a bit of a harder part. You guys understanding what I'm saying? Let me know if you guys are clear. All right. Yeah, absolutely. I'm going to get to the Q&A after. So yeah, there's two ideas that you could do to load in your data. Now I'm going to also give you some more tips that I found throughout my experience. So let's say that you are loading in, let's load in 1,000 images. Now, if you load 1,000 images in one complete step, it's going to take a very long time for your program to load in all of those images in one time. In the programming lingo, that's called loading all of the images in one batch. And also, you might not be able to hold all of those images at once in memory. If you're working with a very small system like a Raspberry Pi, your Raspberry Pi might crash because loading in all of those images caused the Pi to run out of memory. So my tip to you is unless you're stuck into loading the images into one batch, I would load data in mini batches. So instead of loading one step of 1,000 images, maybe we'll load 500 images and then another 500 images. Or we could divide it by 4. So we have 250, 250, 250, 250. That way, you're handling a smaller amount of images and we're not going to run out of memory. So it's very nice. And it's very nice to computer. And also, there's an idea of shuffling the files. So once the images are mapped between their image and their label, sometimes the computer can memorize it too much. Like if you're loading all of the benign images at once, the computer might just say, oh, okay, I'm reading all of these images. They're all of benign tumors. Okay, then the next one's going to be a benign tumor. Okay, then all I'm going to do is predict that the next image is a benign tumor. And, the computer will get lazy and it's going to make a lot of mistakes. So the idea is you shuffle the files when they're loaded into the program. So that way, instead of having a long string of benign tumor images, you might have benign tumor, malignant, 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 benign. That way the computer won't get lazy and it'll be able to learn more patterns by being tested more often. And it's exactly what I wrote on the slide. It's not going to remember sequential patterns. Randomness is good. And here's kind of a illustration of the training process. Now, once you've done that and loaded in your data, you have images loaded in to your program, and you have those labels, the most common thing you'll need to do is convert those images into multi-dimensional arrays. Now, you might be saying, oh my God, that's a big word, multi-dimensional arrays. I don't even know. I can't even handle 2 dimensions. I hate geometry. I can't deal with multi-dimensional arrays. Well, it's going to be okay. I'll explain that in the next slide. And it's going to be kind of simple. So what we call a picture can also be described as an intensity array. And here's how I'm going to explain this. So you guys know about the format RGB, which stands for red, green, blue. Red, green, blue refers to channels within an image. And a channel is just basically like, a copy of your image, a width and a length, such as like this image of a face. And each pixel, which is like each little square on this image, has a pixel value between 0 and 255. And for each channel, for each pixel, you get a number between 0 and 255. 0 meaning black and 255 meaning white. Now, in this case, with the color channels, 255 means like as much, let's just say red as you can, and 0 means like as little red as you can. And when you overlap all of the channels, like, if I overlap this row of images right here with 253 red, 14 green, and 165 blue, 253 red means as much red as possible, 14 green means don't put as much green, and 165 blue means put a lot of blue. You add that together, you get this first pixel in the image to the top left. And because an image is made up of these 3 channels with each of these pixel measurements, we can exploit that and use that to our advantage, because machine learning likes numbers, and we need to use numbers for our neural networks. And we'll get to that in a second. I may have ordered this wrong. Yeah, we'll get to that in a second. Now, I think this might be the last question I asked you guys, because we might be running out of time. But if you guys could respond to this really quickly, and just keep in mind the multi-dimensional array idea. If you have a collection of images, let's just continue with this breast cancer example, containing magnified benign and malignant tumors. This one's for throat cancer. What inherent problem would you find in the data? So imagine you are given a bunch of data with a bunch of images of benign and malignant tumors, and you're asked to use a neural network to detect which images are benign. You're going to use a neural network to learn which images are benign and which images are malignant. What problem would you find?
I have an answer, but I don't know if it's correct. I was thinking false negative.
False negative? Yeah, that could be an idea. But this is talking about the data itself rather than the actual classification of it. But that's a good answer. All right. So you guys might not have thought of this, but there's class imbalance. Now, you might be asking, what do you mean class imbalance? Well, think about like going to a hospital. How often, like, if you go to a hospital and they're looking at something weird that might be in your skin, how often is it that it will be cancer? Is it very often? Like, do doctors tell you you're going to have cancer all of the time? Yeah. It's not that common. The doctor is going to tell you in a hospital you have cancer. Often it's going to be, oh, we saw you had a cancer, but we caught it early, so it's not going to affect anything. That would be kind of a benign tumor. And when you're trying to detect cancer in a neural network, the problem is that in your data, there's often going to be an imbalance of benign tumors to malignant tumors. There's going to be a lot of images that contain like, we caught the cancer early, rather than, oh no, you actually have cancer, you have X days to live. This is the idea in machine learning and data analysis called class imbalance, because there is more benign tumors in the data than malignant tumors. The problem is that when you're trying to train a neural network with imbalance, it's going to affect the way the neural network learns, and it's going to learn to predict more of the imbalanced portion of the data. Like, it's going to learn more about benign tumors than it's going to learn about malignant tumors. And we can't have that. We need to have a neural network that's going to predict very good in both, whether a image is malignant tumor or a benign tumor. So the natural question we ask ourselves is, how do we correct this? How do we correct this imbalance in our data, which we can't really change? So we can use the idea called a class weight. Now, in machine learning, usually when the neural network makes a mistake, it's going to penalize itself. So like, oh man, I detected that this image of a tumor was benign, but it was actually malignant. Oh no, it gives itself a penalization or a cost. However, with this idea of a class weight, we can actually tell the neural network to penalize itself more when it makes a mistake on the smaller class. So, if the neural network is trying to predict a malignant tumor, but instead predicts that the malignant tumor is benign, the neural network will instead give itself a greater penalization, say, oh no, we need to correct this immediately. This needs to be changed. The inner workings of the model have to be changed a bit so we don't make this mistake again. So that's the idea of a class weight. And thank you guys for all the questions. I'll be coming to that at the end of the talk. Now, fortunately, there's a formula to create a class weight and to find how much penalty we're going to give the neural network. And that's with this formula right here. I'm going to send you these slides after the presentation, but I think this formula is very good to remember or just keep in mind. And that is W equals N over 2N, capital N over 2N. For N, capital N is the total amount of data you have. So that's like 100 images, 1,000 images. And little n is the amount of data that corresponds to your smaller class. So for example, if we had 1,000 images in total and we only had 100 malignant tumor images, then we could just say that W is equal to 1,000 over 200. And we would find out how much to penalize the model when it makes a wrong decision on predicting the malignant tumor. And all you have to do with this class weight W is just give it to the machine learning model and associate that with the smaller class. So we just tell it, hey, this class weight goes to malignant tumors because we have less of it. And here are some depictions of class imbalance. So you could see this kind of corresponds to cancer. There's a lot more negative diagnoses of cancer than positive. So here's a direct class imbalance. You plot this on a bar chart, or you could plot this on a pie chart. There's a 97% of class 0 and only 3% of class 1. We can't have that. So class imbalance. Thus, we use class weights. We're going to be needing that for our model. The next thing we're going to need to do, remember that multidimensional array idea? We're going to need it right about now. Once you've loaded in that data and you've seen that class imbalance, we're going to need to normalize the data to deal with the wide range of pixel values across the 3 or more channels in the image. We know that a pixel value can take any value between 0 and 255, but that is a large range. And machine learning likes to deal with small numbers, maybe in the range between 0 and 1. And by giving it a large range, it's going to take a while to do the calculations. There might be some mistakes and problems. So what we do is we normalize the pixel values to keep them to smaller range. And the very easy way to do that is by dividing each pixel value in that multidimensional array by 255. And we do 255 because that's the maximum pixel value. No pixel value can go higher than 255 because the allowable range of pixel values goes between 0 and 255. And if you use a library like NumPy, which is a Python library that's very good for dealing with multidimensional arrays, you could just straight up divide the multidimensional array by 255, and it's very easy. And there's an alternative technique. So instead of just converting the picture to a multidimensional array and dividing all of the pixel values by 255 to get our normalized image, you can also use standardization, which is a bit better, I believe, with dealing with outliers. And that does more statistical techniques, such as like subtracting the mean and dividing by the standard deviation. And to show you what I mean, I have an image. So here is this image. You can see before normalization, the range of pixel values is between 1 and 5. And let's say that range is too much. Well, we could do a normalization by dividing each value by 5, and we get this now normalization, which has pixel values between 0 and 1. Now, the math probably is not correct, but you could see the general idea what I'm talking about. Do we have any questions so far pertaining to any of, like, do we have any things we need to address before we move on, guys? Directly about the presentation. Are we all clear? And Gaurav, I'll get to your questions, which are a little bit out of the scope of the presentation, a little later. Okay, thanks guys for sticking around. We're almost getting to the fun part, deep learning. This is a cool trick you can do. It's called augmenting the data. Now, the idea of augmenting the data is, let's say that in real life, when someone is trying to test your deep learning model, and by giving it your model its own, like let's say that you are trying to test my deep learning model, and you're going to snap some pictures. So let's say I have a deep learning model that will detect a dog versus a cat. Now, I trained my model using this picture of a dog, the input image. But let's say that you're mischievous and you turn the picture upside down, and you still want me to detect whether this upside down image of a dog is a dog or a cat. Well, that's a problem because my neural network has not been trained on upside down images. And they might make a mistake and just say that an upside down dog is a cat. We can't have that. But this has been handled already, thanks to the glory of machine learning scientists. There's a thing called an image data generator, and it will just take already existing images and apply small transformations of them. So we have this input image, and what an image data generator will do is it will do different transformations. So we can some transformations we can do is rotate the image 90 degrees, clockwise or counterclockwise. We could flip an image vertically or horizontally. We can translate an image vertically or horizontally, increase the brightness or contrast. We could shear or zoom in. You can see all these augmented images. They're all of this same picture of a dog eating Chinese food. I don't know. And, this one on the bottom right, I think it's been flipped horizontally. And I think this one at the top left, that one might have been sheared. And it's very good because it helps the machine learning model detect slight irregularities in the data, and also detects all of those mischievous people trying to trick your machine learning model. They failed again. So that's augmenting your data. Now, this question is for those who may have experience with neural networks already. And if you do, excellent. But for those who don't, it's completely fine. But for those who do, what type of neural network is best for dealing with images? So like of breast cancer tumors or, throat cancer tumors. And if you're very keen, what type of inner components would you put in this neural network? So I'll give you guys maybe 1 or 2 minutes. All right, so we have some excellent answers in the chat. And these answers include all of the correct answer, which is CNN. And no, that's not the news network. That is called a convolutional neural network. And Marcia, I think that's how you pronounce it. That's also the correct answer as well. Oh, you even put the sub question. You got that convolutions, pooling, and fully connected layers. You're going above and beyond with that. Very nice. And it's exactly, so you guys answered that completely correctly. Exactly. The common type of neural network to use for analyzing patterns and images is a convolutional neural network. Is a convolutional neural network. And for those who are not that familiar with what a convolutional neural network is, it's a specific type of neural network that is able to analyze both small and large patterns in images. So the way how a convolutional neural network works is it's going to try to find some distinguishing item that separates classes. So for example, a dog and a cat. A dog has, I don't know, flappier ears than the cat. So we can kind of analyze this flappierness of the image and use that as a starting point to differentiate dogs and cats. Or, a bulldog probably has a different snout than a cat or a Maine Coon. We can use that as another starting point. And the convolutional neural network will basically just expand and expand and expand until it, sees that, oh yes, this snout is completely different from the snout of a cat. Instead of just looking at a single line. It does this via processes called convolutions and pooling. That's too complicated to talk about right now, but you can look into that on your own time. With healthcare data, this is especially important because all healthcare data is run on images, and convolutional neural networks, they like images. And they're the fastest at dealing with images. And fast classifications lead to rapid pre-diagnosis. So, you're going to get your cancer result early. And of course, you want that negative. That's a picture of a convolutional neural network. And here is kind of an image of how you would craft a convolutional neural network. This is from my own research paper. You can see some key distinguishing factors for a convolutional neural network. You have conv2D, basically our convolutional layer. You have our activation layer, which is ReLU, a version of that called leaky ReLU. I'll get to that. And you have your pooling, and all the others is just flavoring. So although a custom crafted convolutional neural network could be very good, it may sometimes be easier to use a pre-trained CNN, because you may know the stuff about convolutional neural networks, and you may know how many convolutional layers to put. You may know how many pooling layers to put. You may know how many batch normalization layers to put. But usually that stuff is experimental. If you use a pre-trained neural network, which is a neural network that's already been compiled and trained on a specific training set, so like ResNet, VGG16, or EfficientNet. EfficientNet is also pretty good. You're going to probably get a greater accuracy, and you're also going to get, it's also going to train less because it's already been trained on some stuff. However, a word of warning for pre-trained neural networks, if your brain is still remembering, packing in all this information, it's up to you to customize the inputs and outputs of the neural network to work with your data set. These pre-trained neural networks, they have been trained to work on some other type of data. So for example, I know that ResNet has been trained on the ImageNet database, which is like a lot of different types of images, not specifically cats and dogs. So it's up to you to change some things like the weights and the input of the pre-trained model so it works with your data. So there's going to be a little bit of shipping and handling with pre-trained models instead of just getting one for free. And here you can kind of see a depiction of all different types of pre-trained models we have so far. Operations means how long it takes, and accuracy is pretty self-explanatory. And you can see kind of the different types of pre-trained neural networks. I like VGG16. ResNet is also very good. All right, now we're going to talk about optimizing your neural network, because having a good old neural network, that's pretty good, but we can make it even better. We can put that special oil inside the car to make it run even faster. And we want that. We want our neural network to run like a car, a brand new Porsche. Here's some ideas you could do. The first thing is fine-tuning layers of a pre-trained neural network. Instead of just taking the pre-trained neural network as is, you can do some fine-tuning. And it leads to the neural network learning more specific patterns of your task, because it's going to retrain, learn new things instead of just using the things it's already learned. You could use tuned versions of the ReLU activation layer. This is more technical. It avoids a problem called dying ReLU, where if the, which is more of a math thing, but for those mathematically inclined, it deals with if the gradient is too low, dying ReLU will just keep on printing out zeros and the model won't learn anything. I recommend you to use leaky ReLU or ELU activation. Very good activation. You could use early stopping in model checkpoints. Early stopping is an idea in machine learning where you could save some CPU, GPU usage on the computer if the model doesn't improve that much. And model checkpoints is sort of like stopping the model halfway through and keeping a track of how much the model has learned in that time. So if you know your neural network is going to need to be trained in 6 hours, well, you could train it for 3 hours, give it set a checkpoint, and then return to training it in another 3 hours, and it'll be fully trained. And this is pretty important right here, is creating a constant in the data that reflects the class imbalance, which is called an output bias. Now, I already talked about using class weights, but this is another idea. This output bias will speed up the convergence, which is like how quick the neural network runs, and eliminate training periods in the neural network where the network is just learning, oh, hey, there's a class imbalance. And there's a formula. It is this formula. P stands for the positive class, N stands for negative class. I believe log is the binary logarithm. All right. And here you can see a depiction of early stopping, because the error on the validation set, which is the neural network is going to be trained on, like how good it's doing, is starting to go up, and error should not go up. Okay, we're almost done, guys. We can do it. We only got a small amount of slides left. Who's excited to finish? I know I am. And if you still have any questions, you can pop them in the Q&A. Now, this part is really important, and you guys should be, if you're taking notes, this is an important part to take notes on. How do we, inform some random Joe Schmo that, hey, I did a machine learning and it gave me good results, and I can show you it's certifiably good? We do this using metrics. Metrics are basically just like, how good the neural network is. And there's a couple metrics you should be aware of. The first thing is validation accuracy. Validation accuracy is the accuracy on the neural network's classifications on a set of data that the neural network has never seen. Usually what you do with your healthcare data is you're going to split it into 2 sets. You have your training data, which is what the neural network is going to learn from, and you have your validation data, which is some data that the network has not seen yet. And the idea is that the validation data is going to reflect the true nature of how good your neural network is. And by definition, validation accuracy is how accurate the neural network is. And it's good because it kind of generalizes a bit out of its training data. And the most common thing you're going to probably report is validation accuracy. There's also precision. This one's less used, but that's basically how the metric that measures how much of the classifications made of one class are correct. So, if you have 50% cancer diagnosis precision, that means that when the model predicts a cancer cell's malignance, it's correct 50% of the time. There's recall, which measures how much of the actual class was identified by the model. So 11% cancer diagnosis recall means that the network can correctly identify 11% of all malignant tumors in the data. It's pretty horrible. I don't know what else it predicts. And there's AROC. These two, validation accuracy and AUROC, most important things you're going to need to know. And AUROC stands for the area under the receiving operating characteristic curve. I just call it the area under the ROC. And that's a measure of how well your neural network can effectively distinguish between two classes. So can a neural network effectively distinguish between benign tumors and malignant tumors? Well, you answer that by finding the area under the ROC curve. And you can actually plot this ROC curve, and the better your classifier, the more it's going to say to the top left. In addition to stating that my neural network has 98% validation accuracy, you could also show graphs, because who doesn't like graphs? Every scientist loves graphs. You could easily do this with graphing libraries like Matplotlib, Seaborn, and Bokeh. I like using Matplotlib and Seaborn. And some common choices of plotting the data so scientists can eat with their eyes as a plot of your neural network's training and validation accuracy, a plot of the neural network's training and validation loss, a plot of the neural network's architecture, and possible visualizations of your data and showing, what did my neural network predict and what was the actual label? So you could show how your neural network performs on a specific data point. And let's take a look at some few examples. So this image is from the famous LeNet paper published by Yann LeCun. Yann LeCun is a very famous scientist at NYU. He created this architecture. He's kind of, I think, one of the originators of the convolutional neural network, and he created a structure called LeNet. And in order to show all of those scientists, hey, look at my architecture, he put it in his paper. So this is a figure of the neural network architecture, which is a CNN, contains your convolutions, your pooling, subsampling means pooling, and you have your dense layers called fully connected layers. And this is a result from my own research paper. Can anyone tell me? It's a simple bar graph, but can anyone tell me what this bar graph may represent? Yes, so the bar graph represents the data sets. So as Gaurav said and Marcia said, you have the specific data sets. We have a cancer imaging archive, TCIA, and you have another data set called PatchChemoyon. And basically, these data sets have different magnifications of cancer. So one of it has 20 times magnification on the cancer tumor cells, and the other has 40 times magnification. And I was trying to detect whether this magnification had any effect. And you can see the accuracy, and it turns out, I believe that greater magnification, this pink one was 40 times, had a better accuracy of prediction than the TCIA, which is like 20 times magnification. You also have to keep in mind the error bars. If the error bar is oversect, you got to do some t-tests to make sure that the result is statistically significant. So statistics is still here. You can't ignore statistics. Now, I did all of this without mentioning any type of code. I mentioned libraries, but I didn't talk about any type of code. So if you're interested in seeing how I was able to create a research paper using a custom crafted CNN. Oh, stop moving. On detecting real world breast cancer tumor images with lymph nodes. I have a collab notebook just on my GitHub. I can, I think, paste that for you in the chat a little later. And it makes use of a lot more advanced techniques, but everything I said here still applies there. Yeah, that's it. Thank you for listening to my presentation. I hope you guys enjoyed it, and I had a lot of fun making it. And now I will answer your questions. And yeah, that's my website. I'll pop that in the chat if you guys want to take a look at what else I've done.
Okay, that's really great. Thank you for your workshop. It was really interesting, and I'm pretty sure the people in our audience today learned a lot. Thank you for it.
Yeah, it's really great for having me. Thank you.